We think we understand gravity. It holds our feet to the Earth. It keeps the moon circling above. It binds galaxies together across billions of light years. But there's a deeper question few ever ask. How fast does gravity move? For centuries, we assumed it was instant. Then Einstein told us it wasn't. He said gravity, like light, is limited, bound by the same cosmic speed limit. But how do we know? Could we be wrong? Could gravity reach across space faster than we've ever imagined? Or does its speed tell us something far more profound about the nature of reality itself? In this documentary, we follow the evidence, the history, and the frontiers of physics to answer a question that goes beyond science, a question about how the universe truly connects. Look up at the night sky. Every star you see, every planet in our solar system, every galaxy spinning in the cosmic dance above us, they're all held together by an invisible force that reaches across the vastness of space. Gravity. It's the architect of the universe, sculpting everything from the gentle curve of Earth's orbit around our sun to the violent spiral of matter falling into a black hole. For over 300 years, we thought gravity worked instantly. Isaac Newton imagined it as an invisible hand that could reach across millions of miles in no time at all. If our sun suddenly vanished, Newton believed Earth would immediately fly off into space, feeling the loss of gravity's pull in the same instant the sun disappeared. But Albert Einstein changed everything. In 1915, he revealed that gravity isn't a force reaching through empty space. Instead, it's the bending and warping of space and time itself. And just like everything else in our universe, these ripples in space-time move at a very specific speed, the speed of light. Not faster, not slower, but exactly the same speed that light travels through the vacuum of space. This means gravity has a speed limit. When massive objects accelerate or collide somewhere in the universe, they send waves through the fabric of space-time itself, racing outward at roughly 300,000 kilometers per second. These gravitational waves carry the news of cosmic events across the universe, but they can never arrive before light from those same events. But here's the question that keeps physicists awake at night. How do we really know this is true? What if gravity could somehow slip through space faster than light? What if there are shortcuts through dimensions we can't see, allowing gravitational influence to outrun the cosmic speed limit? And what would it even mean for our understanding of reality if gravity could move faster than light itself? This isn't just an academic puzzle. The speed of gravity touches the very foundations of how we understand time, space, and causality. It determines whether the future can influence the past, whether information can travel backward through time, and whether the orderly sequence of cause and effect that governs our everyday experience holds true across the entire cosmos. To understand this mystery, we must begin with how we learned gravity moves at all. Picture Isaac Newton sitting beneath an apple tree in 1666, watching fruit fall to the ground. This moment, whether real or legend, sparked one of history's greatest insights about gravity. But Newton's brilliant mind was also deeply troubled by what his own theory implied about how gravity actually worked. Newton's law of universal gravitation, published in 1687, described gravity as a force that acts instantly across any distance. Earth pulls on the moon, the sun pulls on Earth, and every massive object in the universe pulls on every other massive object, with a force that depends on their masses and the distance between them. But here's what bothered Newton himself. This force seemed to act instantaneously, no matter how far apart the objects were. Imagine the sun suddenly doubling in mass. According to Newton's theory, Earth would immediately feel a stronger gravitational pull, even though the sun is 93 million miles away. The change would happen faster than light could travel from the sun to Earth. Newton called this idea of action at a distance absurd and admitted he had no explanation for how gravity could work this way. He famously wrote, "I do not feign hypotheses about the mechanism behind gravitational attraction." For over 2 centuries, Newton's mathematics worked beautifully. Scientists could predict planetary orbits, calculate the paths of comets, and even discover new planets like Neptune by observing gravitational effects on other celestial bodies. The theory was so successful that most physicists accepted instant gravitational action as simply how the universe worked, even if they couldn't explain why. But cracks began to appear in Newton's gravitational edifice. Mercury, the closest planet to our Sun, didn't orbit exactly where Newton's equations predicted it should. Its elliptical orbit slowly rotated around the Sun in a way that Newtonian gravity couldn't fully account for. Scientists proposed various explanations, including the possibility of an undiscovered planet called Vulcan orbiting even closer to the Sun, but none of these ideas panned out. Then came Albert Einstein, a young patent clerk in Switzerland, who would revolutionize our understanding of space, time, and gravity itself. In 1905, Einstein published his special theory of relativity, which established that nothing in the universe can travel faster than the speed of light. This created a fundamental problem for Newton's instant gravity. How could gravitational effects propagate instantaneously when nothing else could exceed light speed? Einstein spent the next 10 years wrestling with this puzzle, developing what would become his masterpiece, the general theory of relativity. Published in 1915, this theory completely reimagined what gravity actually is. Instead of a mysterious force reaching across empty space, Einstein revealed that gravity is the curvature of space-time itself. Picture a stretched rubber sheet with a heavy bowling ball placed in the center. The ball creates a depression in the sheet, and if you roll marbles around this depression, they'll follow curved paths, spiraling inward toward the bowling ball. Einstein showed that massive objects like stars and planets do something similar to the fabric of space-time, creating curves and warps that other objects follow as they move through the universe. This geometric view of gravity solved the speed problem elegantly. When a massive object accelerates or changes, it creates ripples in the curvature of space-time that spread outward at exactly the speed of light. These ripples, which Einstein called gravitational waves, carry information about the changing gravitational field from one place to another. Gravity doesn't act instantly anymore. It propagates at light speed through the warped geometry of space-time. Einstein's theory also perfectly explained Mercury's orbital precession. The intense curvature of space-time near the Sun caused Mercury's orbit to slowly rotate in exactly the way Einstein's equations predicted. This was the first major victory for general relativity, proving that Einstein's geometric gravity was more accurate than Newton's instant force. But Einstein's gravitational waves remained a theoretical prediction for nearly a century. The effects are incredibly tiny, requiring the most sensitive instruments ever built to detect them. Einstein himself doubted whether these ripples in space-time would ever be directly observed. He couldn't have imagined that future scientists would build detectors capable of measuring changes in distance smaller than 1/10,000th the width of a proton. The transition from Newton's instant gravity to Einstein's light-speed gravity represents one of the most profound shifts in scientific thinking. It transformed gravity from a mysterious force into a manifestation of curved space-time, subject to the same speed limits that govern light and all other forms of information in our universe. Yet this raises a deeper question that continues to fascinate physicists today. How can we be absolutely certain that gravity doesn't move faster than light? What experiments can definitively test the speed at which gravitational effects propagate through the universe? The answer to this question would require some of the most sophisticated scientific instruments ever conceived. The implications of Einstein's speed limit for gravity extend far beyond academic physics. If gravitational effects truly propagate at light speed, then the universe operates according to a fundamental principle of causality. Events can only influence other events if there's enough time for information to travel between them at the cosmic speed limit. This means the future cannot influence the past, and cause must always precede effect throughout the cosmos. But what if Einstein was wrong? What if gravity found ways to slip through space faster than light, carrying information about distant events before light from those same events could arrive? Such faster-than-light gravity would shatter our understanding of time and causality, potentially allowing effects to precede their causes and creating paradoxes that would fundamentally challenge our perception of reality. Consider the practical implications. Right now, as you read these words, you're experiencing Earth's gravity as it exists in this moment. But the Sun's gravitational influence on our planet reflects the Sun's mass and position as it was about 8 minutes ago, the time it takes light to travel from the Sun to Earth. If the Sun suddenly vanished, we would continue orbiting normally for 8 minutes until the gravitational waves carrying news of the Sun's disappearance finally reached us, arriving at the same time as the last light from our vanished star. This delayed gravitational response shapes everything from the stability of planetary orbits to the evolution of binary star systems. When two massive stars orbit each other, they gradually spiral inward as gravitational waves carry away energy from their orbital motion. The speed of these waves determines how quickly the stars lose energy and how long it takes for them to eventually collide in spectacular explosions that can be seen across billions of light years. Einstein's geometric view of gravity also revealed something profound about the nature of space and time themselves. In Newton's universe, space was like an empty stage where gravitational forces acted between distant objects. But Einstein showed that space and time form a dynamic, flexible fabric that can be stretched, compressed, and rippled by the matter and energy within it. Gravity isn't something that acts in space-time. Gravity is the curvature of space-time itself. This understanding fundamentally changed how physicists think about the universe. Every massive object, from subatomic particles to supermassive black holes, continuously shapes the geometry of space-time around it. When these objects accelerate or change, they send gravitational waves racing through the cosmic fabric at light speed, carrying energy and information about their motion to distant corners of the universe. The mathematics of general relativity make specific predictions about how these gravitational waves should behave. They should propagate at exactly the speed of light, carry energy away from their sources, and produce incredibly tiny but measurable effects on sensitive detectors. For decades, these predictions remained unconfirmed, existing only in the abstract realm of Einstein's elegant equations. The mathematics of general relativity make specific predictions about how these gravitational waves should behave. They should propagate at exactly the speed of light, carry energy away from their sources, and produce incredibly tiny but measurable effects on sensitive detectors. For decades, these predictions remained unconfirmed, existing only in the abstract realm of Einstein's elegant equations. But the transition from Newton to Einstein wasn't just a change in mathematical formalism. It represented a complete philosophical shift in how we understand the relationship between matter, space, and time. Newton viewed space as an absolute unchanging arena where objects moved and forces acted. Time flowed uniformly throughout the universe, providing a cosmic clock that ticked at the same rate everywhere. Einstein's revolution shattered these intuitive notions. Space and time became relative, their measurement depending on the observer's motion and position in gravitational fields. A clock near a massive object runs slower than an identical clock in weaker gravity. Distances contract and expand depending on relative motion. the universe revealed itself to be far stranger and more interconnected than Newton could have imagined. This interconnectedness extends to gravity itself. In Einstein's universe, every change in matter or energy creates ripples that propagate outward through space-time, connecting distant events in a cosmic web of cause and effect. When a massive star collapses into a black hole billions of light years away, gravitational waves from that cataclysm eventually wash over Earth, carrying information about events that occurred long before our planet formed. These waves are extraordinarily weak by the time they reach us. A gravitational wave passing through Earth might stretch and compress space by less than 1 part in 10 to the 21st power. To put this in perspective, if you could measure the distance from Earth to the nearest star with this precision, gravitational waves would change that measurement by less than the width of an atomic nucleus. The weakness of gravitational waves creates both a challenge and an opportunity for physicists. The challenge lies in building detectors sensitive enough to measure such tiny effects against the background noise of seismic vibrations, thermal fluctuations, and countless other disturbances. The opportunity comes from the fact that gravitational waves can travel through the universe almost unimpeded, carrying pristine information about their sources across billions of years and billions of light years. Unlike light, which can be absorbed, scattered, or blocked by matter, gravitational waves pass through planets, stars, and entire galaxies with virtually no interaction. They provide a direct window into the most violent and energetic events in the universe, from the collision of black holes to the first moments after the Big Bang itself. Einstein's prediction of gravitational waves also revealed something profound about the nature of gravity itself. Unlike electromagnetic waves, which are disturbances in electric and magnetic fields propagating through space, gravitational waves are disturbances in the fabric of space-time itself. They don't travel through space, they are the stretching and squeezing of space as they pass by. This distinction has profound implications for understanding gravity's speed. When we say gravitational waves travel at the speed of light, we're really saying that changes in the curvature of space-time propagate at this fundamental cosmic speed limit. It's not that gravity particles or force carriers zoom through empty space at light speed. It's that the geometric properties of space-time itself evolve and change according to the same universal speed limit that governs light. The prediction that gravity moves at light speed also connects to deeper principles in physics. Einstein's theory of relativity established that the speed of light in vacuum represents more than just how fast photons travel. It's a fundamental feature of space-time geometry, determining the relationship between space and time coordinates and setting the maximum speed at which any cause can influence any effect. If gravity moved faster than light, it would violate this fundamental structure of space-time, potentially allowing information to travel backward in time and creating logical paradoxes. The consistency of relativity theory requires that gravitational effects, like all other physical influences, respect the cosmic speed limit established by the geometry of space-time itself. But despite Einstein's confident predictions, proving that gravity actually moves at light speed would require evidence that wouldn't arrive for nearly a century. The story of how scientists finally measured gravity's speed involves some of the most ambitious and ingenious experiments in the history of science, pushing the boundaries of technology and human ingenuity to detect the faintest whispers of space-time itself. For 100 years after Einstein published his theory of general relativity, gravitational waves remained purely theoretical. Einstein himself had doubts about whether these ripples in space-time would ever be detected directly. He calculated that even the most violent cosmic events would produce waves so weak that no conceivable instrument could measure them. He was almost right. The challenge of detecting gravitational waves is nearly impossible to comprehend. These disturbances in space-time are so subtle that they would change the distance between Earth and our Sun by less than the width of a hydrogen atom. Detecting such minuscule changes requires isolating the measurement from every possible source of interference, from earthquakes happening thousands of miles away to the thermal vibrations of individual atoms in the detector itself. The breakthrough came from an ingenious design called a laser interferometer. Picture two perpendicular arms, each several kilometers long, with mirrors at the ends and laser light bouncing back and forth between them. When a gravitational wave passes through this setup, it stretches space in one direction while compressing it in the perpendicular direction. By comparing the time it takes light to travel down each arm, scientists can detect the incredibly tiny changes in distance that gravitational waves produce. But building such a detector requires solving thousands of engineering challenges. The mirrors must be isolated from vibrations so completely that they effectively float in space, suspended by complex systems that filter out disturbances from seismic activity, temperature changes, and even the subtle pressure of photons hitting the mirror surfaces. The laser light must be so stable and pure that any changes in its properties can be distinguished from the effects scientists are trying to measure. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, represents one of the most ambitious scientific instruments ever constructed. Built at two locations in Louisiana and Washington State, each detector consists of two 4-kilometer-long arms arranged in an L shape. Laser light travels down these arms, bouncing between mirrors suspended in ultra-high vacuum chambers, while sophisticated electronics monitor for the telltale signature of passing gravitational waves. When LIGO began operations in the early 2000s, many scientists expected it would take years or decades to make the first detection. Gravitational waves strong enough for LIGO to detect would come from the most extreme events in the universe, such as black holes or neutron stars spiraling into each other and colliding. Such events were thought to be rare, perhaps occurring only once every few years in the volume of space that LIGO could observe. Then, on September 14, 2015, both LIGO detectors simultaneously registered a signal that would change astronomy forever. For just 0.2 of a second, the detectors measured a characteristic pattern of space-time stretching and compressing that perfectly matched Einstein's predictions for gravitational waves from two colliding black holes. The source of these waves was located over 1 billion light-years from Earth, where two black holes, each about 30 times more massive than our Sun, had been spiraling toward each other for millions of years. In their final moments, these black holes accelerated to incredible speeds, reaching over half the speed of light before merging into a single, larger black hole. The collision converted an amount of mass equal to 3 suns directly into gravitational wave energy, creating the most powerful burst of gravitational radiation ever detected. This first detection proved that gravitational waves exist and travel at exactly the speed Einstein predicted. But an even more dramatic confirmation was yet to come. On August 17, 2017, LIGO detected gravitational waves from a completely different type of cosmic collision, one that would provide the most precise measurement of gravity's speed ever achieved. The source was a pair of neutron stars, incredibly dense objects formed when massive stars collapse at the end of their lives. Each neutron star packed more mass than our Sun into a sphere only about 20 kilometers across, creating gravitational fields so intense that a teaspoon of neutron star material would weigh as much as Mount Everest on Earth. Unlike black hole mergers, which produce only gravitational waves, the neutron star collision designated GW 170817 generated both gravitational waves and intense bursts of light across the entire electromagnetic spectrum. This cosmic catastrophe created a kilonova explosion, forging heavy elements like gold and platinum in the extreme conditions of merging neutron star matter. The gravitational waves from this event reached Earth first, detected by LIGO, and its European counterpart Virgo. Then, just 1.7 seconds later, NASA's Fermi Space Telescope detected a burst of gamma rays from the same direction. Within hours, telescopes around the world were observing the optical afterglow of the explosion, confirming that the gravitational wave and electromagnetic signals came from the same source. This simultaneous detection of gravitational waves and light from the same event provided an unprecedented test of gravity's speed. The neutron stars were located approximately 130 million light-years from Earth, meaning their gravitational waves and light had been traveling through space for 130 million years before reaching our detectors. If gravitational waves traveled even slightly faster or slower than light, the signals would have arrived at noticeably different times after such a long journey. The fact that they arrived within less than 2 seconds of each other, after traveling for 130 million years, constrains the speed of gravitational waves to within a few parts per trillion of the speed of light. This measurement represents one of the most precise tests of Einstein's theory ever performed. It confirms that gravity propagates at the speed of light to extraordinary accuracy, ruling out alternative theories that predict different speeds for gravitational effects. The precision of this measurement is equivalent to timing a race between two runners who finish a marathon within 1,000th of a second of each other. But the significance of GW 170817 extends beyond just measuring gravity's speed. This detection launched the era of multi-messenger astronomy, where scientists observe cosmic events using both gravitational waves and traditional electromagnetic signals. By combining information from both types of waves, astronomers can learn far more about distant objects than either method alone could reveal. The gravitational waves carry information about the masses, spins, and orbital dynamics of the merging neutron stars, while the electromagnetic signals reveal details about the explosion, the heavy elements created, and the environment surrounding the collision. Together, these complementary observations provide a complete picture of one of the most violent events in the universe. The success of gravitational wave astronomy has also confirmed many other predictions of Einstein's theory. The waves arrive with exactly the polarization patterns that general relativity predicts. Their frequencies evolve over time in precisely the way Einstein's equations describe for accelerating massive objects. Every detail of the detected signals matches the theoretical expectations for space-time waves traveling at light speed. Perhaps most remarkably, gravitational wave detectors have revealed a universe far more dynamic and violent than astronomers previously imagined. Black hole mergers, once thought to be incredibly rare events, are now detected regularly, suggesting that the universe is filled with these cosmic collisions. Each detection provides new insights into the behavior of matter and space-time under the most extreme conditions possible. The measurement of gravity's speed through gravitational wave astronomy represents the culmination of a century-long quest to test one of Einstein's most profound predictions. From the theoretical insights of 1915 to the technological marvels of the 21st century, this achievement demonstrates humanity's ability to probe the deepest mysteries of the cosmos using ingenuity, precision, and an unwavering commitment to understanding the fundamental laws that govern our universe. Yet even with this triumph, questions remain about the nature of gravity and its relationship to the other forces of nature. The detection of gravitational waves has opened new windows into the cosmos, but it has also revealed new puzzles that continue to challenge our understanding of space-time, causality, and the ultimate structure of reality. The detection of gravitational waves traveling at light speed wasn't just a confirmation of Einstein's predictions, it was validation of one of the most fundamental principles governing our universe. But why should gravity be bound by the same speed limit as light? What deeper connection links these seemingly different phenomena, and what would it mean for reality itself if gravity could somehow exceed this cosmic speed limit? To understand why gravity must move at the speed of light, we need to dive into the heart of Einstein's revolutionary insight about the nature of space and time. The speed of light isn't really about light at all. It's about the fundamental structure of space-time itself, a cosmic speed limit that governs how cause and effect propagate throughout the universe. In Einstein's special theory of relativity, the speed of light in vacuum represents something far more profound than just how fast photons travel. It's the speed at which space-time coordinates transform from one reference frame to another. It's the maximum rate at which any information or influence can propagate from one point to another. It's woven into the very fabric of how space and time relate to each other in our universe. This cosmic speed limit emerges from a simple but revolutionary principle. The laws of physics must be the same for all observers moving at constant velocities relative to each other. This might seem obvious, but it has profound consequences. It means that there's no absolute reference frame, no universal standard of rest that defines how fast things are really moving through space. When Einstein worked out the mathematical consequences of this principle, he discovered that space and time are not separate, independent entities as Newton had assumed. Instead, they form a unified four-dimensional fabric called space-time, where the measurement of distances and time intervals depends on the relative motion between observer and observed. The speed of light emerges naturally from this geometry as the conversion factor between space and time coordinates. Just as there are conversion factors between different units of measurement, like meters and feet, there's a fundamental conversion factor between space and time in the structure of space-time itself. That conversion factor happens to be the speed of light, approximately 300,000 kilometers per second. This deep connection between space-time geometry and the speed of light means that any phenomenon that involves the structure of space-time itself must respect this fundamental speed limit. And gravity, as Einstein revealed in his general theory of relativity, is precisely such a phenomenon. Gravity is the curvature of space-time, so changes in gravitational fields must propagate at the speed that governs all changes in space-time structure. Consider what would happen if gravity could somehow propagate faster than light. Such faster than light gravitational effects would violate the fundamental symmetries of space-time, creating a preferred reference frame, where gravitational influences could be observed to travel at different speeds depending on the observer's motion. This would shatter the principle of relativity and create logical contradictions in the laws of physics. The speed limit also preserves causality, the orderly relationship between causes and effects that governs our everyday experience. If information could travel faster than light, it would be possible for effects to precede their causes from certain reference frames. An observer moving at high speed relative to a faster than light signal might see the effect happening before the cause, creating paradoxes that would undermine the logical structure of physical law. Imagine if gravity could act instantaneously, as Newton believed. An observer moving at high speed toward a massive object would see gravitational effects from that object's future position, while an observer moving away would see effects from its past position. Different observers would disagree not just about when things happened, but about the very sequence of cause and effect. The ordered progression of time would become meaningless. Einstein's insight that gravity is space-time curvature elegantly resolves this problem. When a massive object accelerates or changes, it doesn't send out gravitational force particles at superlight speeds. Instead, it creates ripples in the curvature of space-time itself. And these ripples propagate outward at exactly the speed that governs all changes in space-time geometry, the speed of light. This connection runs even deeper than might first appear. In Einstein's theory, matter and energy don't just move through space-time, they actively shape its geometry. The distribution of mass and energy determines how space-time curves, while the curvature of space-time determines how matter and energy move. This intimate relationship means that changes in matter must communicate with changes in space-time curvature at a speed that preserves the consistency of both. The mathematical framework of general relativity makes this connection precise. Einstein's field equations relate the curvature of space-time at each point to the distribution of matter and energy at that same point. But when matter moves or energy flows, the curvature must adjust accordingly, and these adjustments propagate outward as gravitational waves at light speed. This propagation speed isn't arbitrary or coincidental. It emerges directly from the mathematical structure that relates space, time, matter, and energy in Einstein's theory. Change the speed of gravitational wave propagation, and you would have to change the fundamental relationships between these basic concepts, potentially undermining the entire theoretical framework that successfully describes everything from atomic clocks to black holes. The speed of light also appears as a fundamental constant in the equations that describe electromagnetic phenomena. Light waves, radio waves, and all other forms of electromagnetic radiation propagate at this same speed through vacuum. This isn't a coincidence. Both gravitational and electromagnetic waves represent disturbances in fundamental fields that pervade space-time, and both types of waves must respect the basic speed limit imposed by space-time geometry. But there's an even deeper connection. In modern physics, we understand both gravity and electromagnetism as gauge theories, mathematical frameworks that describe how fundamental symmetries of nature give rise to forces and interactions. These symmetries are intimately connected to the structure of space-time, and they naturally lead to wave equations whose solutions propagate at the fundamental speed limit of space-time itself. The requirement that gravity move at light speed also connects to one of the most profound principles in physics, general covariance. This principle states that the laws of physics must have the same form in all coordinate systems, regardless of how we choose to describe positions and times. General covariance is what allows Einstein's theory to handle accelerated motion and curved space-time, but it also constrains the possible speeds at which gravitational effects can propagate. If gravitational influences could travel at different speeds in different coordinate systems, the principle of general covariance would be violated. The mathematical consistency of Einstein's theory requires that gravitational waves propagate at a speed that's the same in all coordinate systems, and that speed is necessarily the fundamental speed limit of space-time. This web of connections between gravity, light, causality, and space-time geometry creates a remarkably robust theoretical structure. Each element supports and constrains the others, creating a consistent picture of how information and influence propagate through the universe. The speed of gravitational waves isn't just a prediction of Einstein's theory. It's a necessary consequence of the deep symmetries and principles that govern the behavior of space, time, and matter. Yet despite this theoretical foundation, some physicists have wondered whether there might be loopholes, subtle ways that gravitational effects could somehow circumvent the light speed barrier under special circumstances. The possibility of faster-than-light gravity has been explored in various alternative theories and speculative models, each attempting to find ways around the seemingly ironclad constraints of relativity. These explorations have led to some of the most exotic and mind-bending ideas in modern physics. The robustness of the light speed limit for gravity becomes even more apparent when we consider how it emerges from multiple independent lines of reasoning. The speed isn't just imposed by theoretical considerations, it's demanded by the internal consistency of the mathematical framework that describes space-time, matter, and energy. Consider the concept of simultaneity, the idea that events separated by a distance can happen at the same time. In Newton's absolute space and time, simultaneity was universal. If two events happened simultaneously in one reference frame, they were simultaneous for all observers everywhere. But Einstein's relativity revealed that simultaneity is relative. Different observers moving at different velocities will disagree about whether distant events occur at the same time. This relativity of simultaneity is intimately connected to the finite speed of light, and by extension, the finite speed of gravitational effects. If gravity acted instantaneously, it would provide a way to define absolute simultaneity throughout the universe. An observer could, in principle, use instantaneous gravitational signals to synchronize clocks at distant locations, creating a universal standard of now that would contradict the relative nature of time in Einstein's theory. The finite speed of gravitational propagation preserves the relative nature of time by ensuring that no signal, no matter how exotic, can establish absolute simultaneity across space. This maintains the democratic principle that no reference frame is privileged over any other, a cornerstone of both special and general relativity. The connection between gravity's speed and causality extends to some of the strangest phenomena in Einstein's theory. Consider black holes, regions of spacetime where gravity becomes so intense that not even light can escape. The boundary of a black hole, called the event horizon, is defined by the condition that light emitted from this surface can just barely escape to infinity. If gravity moved faster than light, the definition of the event horizon would become problematic, potentially allowing information to escape from regions that should be causally disconnected from the outside universe. The consistency of black hole physics depends crucially on the assumption that gravitational effects propagate at light speed. This ensures that the event horizon represents a true causal boundary, separating the interior of the black hole from the external universe in a way that preserves the logical structure of space-time geometry. Similarly, consider cosmology, the study of the universe as a whole. Einstein's equations describe how the geometry of space-time evolves over cosmic time, relating the expansion rate of the universe to its matter and energy content. If gravitational effects could propagate faster than light, the causal structure of cosmological space-time would be fundamentally different, potentially allowing regions of the universe to influence each other across distances that should be causally disconnected. The finite speed of gravitational propagation plays a crucial role in cosmological models, determining which regions of the universe can have been in causal contact since the Big Bang. This affects everything from the observed uniformity of the cosmic microwave background to the formation of large-scale structures like galaxy clusters and cosmic voids. The speed of light also appears as a fundamental constant in quantum field theory, the framework that describes the behavior of particles and fields at the smallest scales. In this context, the speed emerges from the requirement that quantum fields respect the symmetries of spacetime, including the symmetry between different inertial reference frames. Even though we don't yet have a complete theory of quantum gravity, most approaches to unifying general relativity with quantum mechanics preserve the light speed propagation of gravitational effects. This suggests that the connection between gravity's speed and the structure of spacetime runs deeper than classical physics alone, extending into the quantum realm where space and time themselves might be composed of discrete, fluctuating elements. The experimental confirmations of gravity's light speed propagation also validate related predictions about the nature of space-time. The detection of gravitational waves has confirmed that space and time can be stretched and compressed by passing disturbances, exactly as Einstein's geometric theory predicts. These observations provide direct evidence that space-time is a dynamical, physical entity rather than a fixed backdrop for physical events. The polarization patterns of detected gravitational waves match Einstein's predictions precisely, confirming that these disturbances have the mathematical properties expected for ripples in space-time geometry. The waves exhibit the characteristic strain patterns, frequency evolution, and amplitude behavior predicted by general relativity. all consistent with propagation at exactly the speed of light. These observations also constrain possible modifications to Einstein's theory. Any alternative theory of gravity must reproduce the observed properties of gravitational waves, including their propagation speed, to remain viable. The precision of current measurements severely limits the range of possible modifications, ruling out many speculative alternatives that predict different propagation speeds. The connection between gravity and light speed also illuminates the relationship between different fundamental forces. In the standard model of particle physics, electromagnetic interactions are mediated by photons, particles that always travel at light speed. The hypothetical particles that would mediate gravitational interactions, called gravitons, are predicted to also travel at light speed, creating a deep parallel between these fundamental forces. This parallel extends to the mathematical frameworks used to describe both forces. Quantum electrodynamics and general relativity, despite their very different approaches, both lead to wave equations whose solutions propagate at the fundamental speed limit of spacetime. This suggests that the light speed limit reflects something profound about the nature of physical interactions themselves. The universality of the speed limit also connects to conservation laws, fundamental principles that govern how energy, momentum, and other quantities behave in physical systems. The requirement that these conservation laws hold in all reference frames constrains the possible speeds at which influences can propagate between distant parts of a system. Faster than light propagation would violate these conservation principles, leading to logical inconsistencies in the description of physical processes. Perhaps most fundamentally, the light speed limit for gravitational effects reflects the unity of spacetime itself. Space and time aren't separate arenas where different phenomena occur at different speeds. They form an integrated four-dimensional manifold with a specific geometric structure, and all physical processes, from the propagation of light to the dynamics of gravitational fields, must respect this underlying geometric reality. Despite the overwhelming theoretical and experimental support for gravity propagating at light speed, some of the most creative minds in physics have wondered whether there might be exotic scenarios where gravitational effects could somehow exceed this cosmic speed limit. These speculative theories push the boundaries of our understanding, exploring radical possibilities that challenge the very foundations of relativity and space-time. One of the most intriguing possibilities involves the concept of extra dimensions. Our everyday experience suggests that space has three dimensions: length, width, and height, combined with one dimension of time. But some theories in modern physics propose that additional spatial dimensions exist beyond our normal perception, curled up or compactified in ways that make them invisible at ordinary scales. In theories with extra dimensions, gravity might propagate through these hidden dimensions, while other forces remain confined to our familiar three-dimensional space. If the shortest path between 2 points in our three-dimensional world involves a detour through higher dimensional space, gravitational effects could potentially travel this shortcut and arrive faster than light, traveling through normal space. Imagine a sheet of paper representing our three-dimensional space with 2 points marked on opposite sides. Light traveling along the surface of the paper must cover the full distance between these points. But if the paper is folded so that the points come close together in a higher dimension, a signal traveling through the fold could arrive much faster than light traveling along the surface. Some versions of string theory, one of the leading candidates for a theory of quantum gravity, suggest that gravitons, the hypothetical particles that carry gravitational force, might be able to propagate through extra dimensions called the bulk. Meanwhile, photons and other particles would remain trapped on our three-dimensional brain, a lower dimensional surface embedded in the higher dimensional space. If this were true, gravitational signals could potentially take shortcuts through the bulk, arriving at distant locations before electromagnetic signals traveling through normal space. This could create situations where gravitational waves from a cosmic event reach Earth before light from the same event, violating the apparent speed limit that Einstein's theory imposes. However, these extra-dimensional theories face severe constraints from experimental observations. The detection of gravitational waves from neutron star mergers, arriving within seconds of electromagnetic signals after traveling for millions of years, places incredibly tight limits on any extra-dimensional shortcuts. If such shortcuts existed and were accessible to gravitational waves, the time differences between gravitational and electromagnetic signals should be much larger than observed. Another speculative possibility involves violations of Lorentz invariance, the fundamental symmetry that ensures the laws of physics look the same to all observers moving at constant velocities. Einstein's special and general relativity are built on this symmetry, but some theories suggest that at extremely high energies or in exotic conditions, this symmetry might be subtly broken. Lorentz violating theories of gravity might allow gravitational waves to propagate at speeds that differ from the speed of light, potentially exceeding it under certain circumstances. These theories typically introduce preferred directions in spacetime or modify the relationship between energy and momentum for gravitational waves in ways that could permit faster than light propagation. Some of these theories predict that gravitational waves of different frequencies might travel at slightly different speeds, a phenomenon called gravitational dispersion. Just as white light separates into different colors, when passing through a prism, gravitational waves from a distant source might spread out over time if different frequency components travel at different speeds. The search for gravitational dispersion has become one of the key tests for alternative theories of gravity. If gravitational waves exhibited frequency-dependent propagation speeds, it would be detectable in the arrival times of waves from distant sources. High-frequency components might arrive slightly before or after low-frequency components, creating a measurable signature of modified gravitational physics. Current observations show no evidence of gravitational dispersion. Gravitational waves from black hole mergers, which sweep through a wide range of frequencies as the black holes spiral inward, arrive with their frequency components precisely synchronized in the way Einstein's theory predicts. This null result places strong constraints on Lorentz, violating modifications to general relativity. Some theories propose even more exotic possibilities, such as gravitational effects that propagate through parallel universes or alternate dimensions of time. In certain interpretations of quantum mechanics, multiple parallel realities exist simultaneously, potentially allowing information to leak between them under special circumstances. If gravitational fields could somehow access these parallel channels, they might be able to transmit information faster than light in our universe by taking shortcuts through alternate realities. Such scenarios would require radical modifications to our understanding of quantum mechanics and space-time, venturing far beyond the boundaries of established physics. Another speculative idea involves tachyons, hypothetical particles that travel faster than light by having imaginary mass. While tachyons create logical paradoxes in most physical theories, some researchers have explored whether gravitational tachyons might exist under special conditions without violating causality. These tachyonic gravity theories typically predict that faster-than-light gravitational signals would travel backward in time from certain reference frames, creating closed causal loops that could theoretically allow effects to precede their causes. Most physicists consider such scenarios unphysical, but they illustrate the exotic possibilities that emerge when we abandon the light speed limit for gravitational propagation. Quantum gravity theories also open up speculative possibilities for faster-than-light gravitational effects. Some approaches to quantum gravity suggest that space-time itself might be composed of discrete, fluctuating elements at the smallest scales, similar to how matter is composed of atoms. In such theories, the apparent continuity of space-time at large scales would emerge from the statistical behavior of these quantum building blocks. If space-time has a discrete quantum structure, then the propagation of gravitational disturbances might not be bound by the same speed limits that apply to continuous space-time. Quantum tunneling effects might allow gravitational information to jump across gaps in the space-time foam, potentially exceeding the classical speed of light limit. However, most serious approaches to quantum gravity preserve the light speed limit for gravitational effects, even at the quantum level. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, relies crucially on the finite speed of information propagation to maintain logical consistency. Some researchers have explored modified theories of gravity that add extra fields or particles to Einstein's original framework. These modifications might allow gravitational effects to propagate through multiple channels, with some channels potentially exceeding the speed of light, while others remain subluminal. For example, scalar tensor theories add a scalar field to Einstein's purely geometric description of gravity. This scalar field might propagate at a different speed than gravitational waves, potentially allowing some aspects of gravitational interaction to exceed light speed, while preserving causality for the most important gravitational effects. Brane-world cosmology offers another avenue for potentially faster than light gravitational propagation. In these models, our entire observable universe exists on a three-dimensional brane embedded in a higher dimensional space. Gravity can propagate through the full higher dimensional space, while other forces remain confined to the brane. If the brane is curved or warped in the higher dimensional space, gravitational signals might be able to take shortcuts through the bulk that are not available to electromagnetic signals traveling along the brane surface. This could create situations where gravitational effects arrive before electromagnetic signals, despite both traveling at their respective maximum speeds in their accessible dimensions. The experimental test of these exotic theories has become increasingly precise with the advent of gravitational wave astronomy. Each detected gravitational wave provides a new opportunity to search for deviations from Einstein's predictions, including faster than light propagation or other signatures of modified gravity. The neutron star merger GW 170817 provided the most stringent test yet of gravity's propagation speed. The simultaneous arrival of gravitational waves and gamma rays, after traveling for 130 million years, rules out most theories that predict significantly faster than light gravitational propagation. Future gravitational wave detectors will push these tests to even greater precision. The planned LISA space-based detector will be sensitive to gravitational waves from supermassive black hole mergers occurring billions of light years away. Such distant sources will provide even more stringent tests of whether gravitational effects can exceed the speed of light. Despite the creative theoretical possibilities for faster than light gravity, the experimental evidence continues to support Einstein's original insight that gravitational effects propagate at exactly the speed of light. Each new observation strengthens the case that this cosmic speed limit is truly universal, governing not just electromagnetic phenomena, but the propagation of space-time curvature itself. The failure to find faster than light gravitational effects doesn't diminish the value of exploring these theoretical possibilities. By pushing the boundaries of what's conceivable within the framework of physics, these speculative theories help us understand why Einstein's theory works so well and what fundamental principles constrain the behavior of space, time, and gravity throughout the universe. While we can detect gravitational waves with sophisticated instruments like LIGO, gravity itself remains invisible to our everyday senses. We feel its effects constantly, keeping our feet planted on the ground and holding our planet in orbit around the sun. But we never directly perceive gravitational signals traveling through space the way we see light or hear sound. This invisibility raises fascinating questions about how gravitational information actually propagates through the universe. and why we experience gravity so differently from other forces. The key to understanding gravitational information lies in recognizing that gravity isn't really a force in the traditional sense. When you drop a ball, it doesn't fall because some gravitational force particles are pushing or pulling it downward. Instead, the ball simply follows the straightest possible path through the curved spacetime created by Earth's mass. From the ball's perspective, it's traveling in a perfectly straight line. It's the geometry of space and time around it that's curved. This geometric view of gravity fundamentally changes how we think about gravitational information. When we say that gravitational effects propagate at the speed of light, we're really saying that changes in the curvature of spacetime spread outward at this speed. It's not that gravity particles zoom through empty space carrying messages about gravitational fields. It's that the shape of spacetime itself evolves and adjusts according to the cosmic speed limit. Consider what happens when a massive star suddenly collapses into a black hole somewhere in our galaxy. The collapse changes the distribution of mass in that region of space, which must correspond to a change in the curvature of spacetime. But this change can't happen instantly throughout the galaxy. Information about the collapse must propagate outward at the speed of light, carried by gravitational waves that ripple through the fabric of space and time. As these gravitational waves pass by Earth thousands of years later, they carry with them information about the original collapse. The waves tell us about the mass of the original star, the dynamics of its collapse, and the properties of the resulting black hole. This information traveled to us encoded in the stretching and squeezing of spacetime itself, not in the motion of particles or the oscillation of electromagnetic fields. The information content of gravitational waves is remarkably rich. Unlike light, which can be blocked, absorbed, or scattered by matter, gravitational waves pass through planets, stars, and entire galaxies, almost without interaction. They provide a pristine record of the events that created them, carrying information across billions of years and billions of light years with minimal distortion. When LIGO detected the first gravitational waves from colliding black holes, scientists could reconstruct the entire final moments of these cosmic titans. The waves revealed that two black holes, each about 30 times more massive than our Sun, had spiraled toward each other for millions of years before merging in a fraction of a second. The waves carried information about their masses, their spins, their orbital dynamics, and the properties of the final merged black hole. This information was encoded in the precise pattern of space-time stretching and compression that the waves produced as they passed through Earth. By analyzing the frequency, amplitude, and phase evolution of the detected signals, scientists could work backward to understand the physical processes that created the waves billions of years ago and billions of light years away. The fact that this information traveled to us at exactly the speed of light reveals something profound about the nature of causality in Einstein's universe. The black hole collision happened at a specific time and place in space-time. The gravitational waves carrying information about this event then spread outward at light speed, defining an expanding sphere of space-time within which the collision could potentially influence other events. Outside this expanding sphere of gravitational influence, the universe continued evolving as if the collision had never happened. Stars were born and died, galaxies rotated, planets formed, all without any knowledge of the distant black hole merger. Only when the gravitational waves finally arrived did these regions of space-time gain access to information about the collision. This creates a hierarchical structure of causality throughout the universe. Events can only influence other events if there's been enough time for gravitational waves or electromagnetic signals to carry information between them at the cosmic speed limit. The universe is filled with expanding spheres of influence radiating outward from every significant event, creating an intricate web of causal connections that grows more complex with each passing moment. The solar system provides a perfect example of how gravitational information propagates in everyday astronomical contexts. Earth orbits not around where the Sun is now, but around where the Sun was about 8 minutes ago, the time it takes light and gravitational effects to travel from the Sun to Earth. If the Sun were to suddenly disappear, Earth would continue in its current orbit for 8 minutes until the gravitational waves carrying news of the Sun's disappearance finally reached us. This might seem to contradict our intuitive understanding of gravity as an instantaneous force, but it actually explains why planetary orbits are so remarkably stable. The 8-minute delay between the Sun's position and Earth's gravitational response is exactly what's needed to maintain orbital stability as both objects move through space. The finite speed of gravitational propagation doesn't destabilize orbits. It's essential for keeping them stable over cosmic timescales. The same principle applies to binary star systems, where two stars orbit around their common center of mass. As the stars move in their orbits, they create time-varying gravitational fields that radiate energy away in the form of gravitational waves. This energy loss causes the orbital separation to gradually decrease, and the stars spiral slowly inward toward an eventual collision. The rate at which this orbital decay occurs depends precisely on the speed of gravitational wave propagation. If gravitational effects traveled faster than light, binary stars would radiate energy more efficiently and spiral inward more quickly. If gravitational effects traveled slower than light, the energy radiation would be less efficient and the orbital decay would proceed more slowly. Observations of binary pulsars, rapidly rotating neutron stars in close orbits around companion objects, provide exquisite tests of these predictions. The most famous example, the binary pulsar PSRB 1913+16, has been monitored for decades as its orbital period gradually decreases due to gravitational wave radiation. The measured rate of orbital decay matches Einstein's predictions to extraordinary precision, confirming that gravitational effects propagate at exactly the speed of light. The propagation of gravitational information also plays a crucial role in more exotic astronomical phenomena. When matter falls into a black hole, it doesn't disappear instantly from the perspective of outside observers. Instead, gravitational effects from the infalling matter continue to influence the external space-time, carrying information about the matter's properties outward at light speed even as the matter itself crosses the black hole's event horizon. This creates the remarkable situation where information about matter falling into a black hole propagates outward through space-time even after the matter itself has passed beyond the point of no return. The gravitational waves carry a kind of fossil record of the infalling matter, preserving information about its properties in the curvature of space-time surrounding the black hole. The finite speed of gravitational information also affects how we observe and understand cosmic evolution. When we look at distant galaxies through telescopes, we see them as they were millions or billions of years ago, when the light we're receiving was first emitted. Similarly, gravitational effects from these distant objects influence our local region of space-time based on where those objects were when the gravitational information began its journey toward us. This creates a complex tapestry of causality woven throughout the cosmos. The gravitational field we experience at any moment represents the cumulative influence of every massive object in the universe. But that influence is based on where each object was at the time needed for gravitational effects to reach us at light speed. We live in a gravitational now that's actually composed of information from many different thens across cosmic space and time. The study of gravitational information propagation has also revealed deep connections between gravity and thermodynamics, the science of heat and energy flow. Black holes, the most extreme gravitational objects in the universe, appear to have temperatures and entropies that are intimately connected to their surface areas and the information that falls into them. This connection suggests that gravitational information might be subject to the same fundamental limits that govern other forms of information in physics. The holographic principle proposes that all the information contained within a volume of space can be encoded on its boundary, with the maximum information density determined by the area of the boundary measured in units set by the speed of light and other fundamental constants. If the holographic principle is correct, then the propagation of gravitational information is constrained not just by the speed of light, but by deeper principles that limit how much information can be stored and transmitted through space-time itself. This would connect the speed of gravity to fundamental questions about the nature of information, consciousness, and the ultimate structure of reality. The invisible nature of gravitational information creates unique challenges for understanding how gravity connects different parts of the universe. Unlike electromagnetic radiation, which we can see directly with our eyes or detect with radio telescopes, gravitational waves require extraordinarily sensitive instruments to detect. This invisibility means that much of the gravitational information flowing through the universe passes by us completely unnoticed. Yet this gravitational information is constantly shaping the cosmos around us. Every time two black holes collide somewhere in the universe, they send gravitational waves rippling through space-time, carrying energy and information outward at the speed of light. Most of these waves pass through Earth without any observable effect, but they represent a continuous flow of information about the most violent and energetic events occurring throughout the cosmos. On the largest scales imaginable, where galaxies cluster together across billions of light years, and the universe itself expands at an ever-accelerating rate, gravity's finite speed creates some of the most profound limits on what we can ever hope to know about the cosmos. These cosmic horizons, defined by the distance that light and gravitational effects can travel since the beginning of time, represent the ultimate boundaries of observable reality. The expansion of the universe adds a remarkable complexity to how gravitational information travels across cosmic distances. Unlike the static space-time around a star or planet, the fabric of space itself is stretching as the universe grows larger. This expansion affects both electromagnetic radiation and gravitational waves as they journey across the cosmos, stretching their wavelengths and reducing their energies in ways that reveal the deep connections between gravity, geometry, and the evolution of space-time. When gravitational waves from a distant black hole collision travel through expanding space, the waves themselves get stretched along with the fabric of space-time. A gravitational wave that started its journey with a frequency of 100 cycles per second might arrive at Earth with a frequency of only 50 cycles per second, its wavelength doubled by the expansion of space during its billion-year journey. This cosmological redshift affects gravitational waves in exactly the same way it affects light from distant galaxies. The amount of redshift tells us how much the universe has expanded since the waves began their journey, providing a direct measurement of cosmic expansion that complements and confirms observations made with electromagnetic telescopes. But the expanding universe creates an even more fundamental limit on gravitational knowledge, because space itself is stretching, and because this stretching is accelerating due to the mysterious influence of dark energy. There are regions of the universe from which gravitational waves can never reach us, no matter how long we wait. These regions lie beyond our cosmic horizon, forever causally disconnected from our local patch of space-time. The cosmic horizon represents the maximum distance from which light or gravitational waves could have traveled to reach us since the Big Bang occurred nearly 14 billion years ago. But the expansion of space complicates this simple picture. While light and gravitational waves always travel at the same speed locally, the space through which they travel is itself expanding, stretching the distances they must cover and potentially preventing them from ever reaching distant destinations. Consider a gravitational wave emitted by a black hole collision in a galaxy at the edge of our observable universe. As this wave travels toward us, the expansion of space carries its source galaxy ever farther away. If the expansion rate exceeds a critical threshold, the gravitational wave will never be able to overcome the stretching of space to reach us. The wave continues propagating at light speed through its local spacetime, but the destination recedes faster than the wave can approach it. This creates different types of cosmic horizons that limit different aspects of our knowledge about the universe. The particle horizon defines the maximum distance from which light could have reached us since the Big Bang, encompassing everything we can potentially observe with electromagnetic telescopes. The event horizon defines the maximum distance to which we could ever send signals, even if we wait indefinitely into the future. Between these horizons lies a complex landscape of cosmic causality, where some regions remain forever beyond our reach, while others gradually come into causal contact as the universe evolves. The accelerating expansion driven by dark energy is pushing the event horizon closer to us, meaning that regions of space that we can observe today will gradually disappear beyond our causal influence as cosmic time progresses. Gravitational waves provide a unique probe of these cosmic horizons because they can travel through the universe virtually unimpeded. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves pass through matter with almost no interaction. They carry pristine information about events that occurred in the early universe, potentially allowing us to peer closer to the Big Bang itself than any electromagnetic observation could achieve. The cosmic microwave background radiation, the afterglow of the Big Bang, provides our deepest electromagnetic view of the early universe. This radiation was emitted about 380,000 years after the Big Bang, when the universe first became transparent to light. Before this time, the universe was filled with a hot, dense plasma that absorbed and scattered photons, creating an impenetrable electromagnetic fog. But gravitational waves could have traveled freely through this early plasma, carrying information about events that occurred much closer to the moment of the Big Bang itself. A cosmic gravitational wave background, analogous to the cosmic microwave background but composed of gravitational rather than electromagnetic radiation, might contain information about the universe when it was only a fraction of a second old. Detecting this primordial gravitational wave background would provide unprecedented insights into the physics of the very early universe, potentially revealing details about cosmic inflation, the rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. These gravitational waves would carry information about quantum fluctuations in space-time itself, fluctuations that eventually grew to become the large-scale structures we observe in today's universe. The finite speed of gravitational propagation also affects how cosmic structures form and evolve over billions of years. Gravity is the dominant force shaping the large-scale structure of the universe, pulling matter together to form galaxies, galaxy clusters, and vast filamentary networks that span hundreds of millions of light years. But this structure formation process is limited by the speed at which gravitational information can travel. When the universe was very young and much smaller, different regions could communicate gravitationally across relatively short distances. As the universe expanded and these regions became more widely separated, the time required for gravitational effects to travel between them increased correspondingly. This created a hierarchy of structure formation, where smaller objects formed first and later assembled into progressively larger structures. The cosmic web of galaxies and dark matter that we observe today represents the cumulative result of billions of years of structure formation, with each stage limited by the finite speed of gravitational information propagation. Galaxy clusters, the largest gravitationally bound objects in the universe, are still forming today as smaller galaxy groups fall into them along the cosmic web. But this process is constrained by the time it takes gravitational effects to coordinate the motions of matter across such vast distances. Dark energy, the mysterious component that drives the accelerating expansion of the universe, interacts with gravity in ways that further complicate the propagation of gravitational information. As dark energy pushes space to expand faster and faster, it creates an effective horizon beyond which gravitational effects from distant regions can never reach us. This acceleration is gradually isolating our local group of galaxies from the rest of the observable universe. In the far future, as dark energy continues to dominate cosmic evolution, our descendants will find themselves in an increasingly isolated universe. Distant galaxies will disappear beyond the cosmic horizon, their light and gravitational effects redshifted to undetectable levels. The observable universe will shrink to encompass only our local group of galaxies, leaving future astronomers with a much more limited view of cosmic reality. The study of gravitational wave propagation in expanding space-time has also revealed deep connections between gravity and the fundamental constants of nature. The speed of gravitational waves depends not just on the local geometry of space-time, but on the global properties of the cosmic expansion. Changes in the expansion rate, driven by the evolving balance between matter, radiation, and dark energy, subtly affect how gravitational waves propagate across cosmic distances. These effects are incredibly small, but they're potentially detectable with sufficiently sensitive instruments. Future gravitational wave observatories might be able to measure tiny variations in the speed of gravitational wave propagation that reveal details about the history of cosmic expansion and the properties of dark energy. Such measurements could provide independent confirmation of cosmological models developed from electromagnetic observations. The horizon problem in cosmology illustrates another way that gravity's finite speed affects our understanding of the universe. The cosmic microwave background radiation shows that different regions of the sky, separated by distances much larger than light could have traveled since the Big Bang, have nearly identical temperatures. This suggests that these regions were somehow in causal contact in the early universe, despite being too far apart for light or gravitational signals to travel between them. The solution to this puzzle involves cosmic inflation, a period of exponentially rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, regions that are now widely separated were once close enough together for gravitational and electromagnetic effects to travel between them, establishing the uniform conditions we observe today. The finite speed of information propagation, whether by light or gravitational waves, plays a crucial role in understanding how this early causal contact was established and then broken by the subsequent expansion of space. Gravitational lensing provides another window into how gravity's effects propagate across cosmic distances in an expanding universe. When light from a distant galaxy passes near a massive object like a galaxy cluster, the curvature of space-time bends the light's path, creating distorted or multiple images of the background galaxy. This lensing effect depends on the precise timing of how gravitational effects from the intervening mass reach the path of the light. In an expanding universe, both the light from the background source and the gravitational effects from the lensing mass must travel through stretching space, with their relative timing affected by the cosmic expansion. The observed properties of gravitationally lensed objects therefore carry information about both the expansion history of the universe and the speed at which gravitational effects propagate across cosmic distances. The ultimate horizon of gravitational knowledge may extend even beyond the observable universe to encompass speculative ideas about the multiverse, parallel universes, or extra dimensions. If gravity can propagate through dimensions beyond our familiar three-dimensional space, gravitational effects from other universes or alternate realities might theoretically reach us, carrying information about cosmic domains that are otherwise completely inaccessible to observation. However, such ideas remain highly speculative and would require revolutionary advances in both theoretical physics and observational technology to test. The horizons imposed by the finite speed of gravitational propagation in our own universe already represent profound limits on human knowledge, defining the ultimate boundaries of what we can ever hope to learn about the cosmos through direct observation. The detection of gravitational waves has opened an entirely new window into the universe, but we're still in the very early stages of gravitational wave astronomy. The instruments that confirmed Einstein's predictions about gravity's speed represent just the beginning of a technological revolution that promises to test our understanding of space-time, causality, and fundamental physics with unprecedented precision. Current gravitational wave detectors like LIGO and Virgo are sensitive to a specific range of frequencies, roughly 10 to 1,000 cycles per second. This frequency range is perfect for detecting black hole and neutron star mergers, but it represents only a narrow slice of the gravitational wave spectrum. The universe likely produces gravitational waves at much lower and much higher frequencies, carrying information about completely different types of cosmic phenomena. The next generation of gravitational wave observatories will expand our sensitivity across the entire gravitational spectrum, from ultra-low frequency waves with periods of years or decades to high-frequency waves oscillating thousands of times per second. Each frequency range opens up different aspects of the universe to investigation, and each provides new opportunities to test whether gravitational effects truly propagate at exactly the speed of light. LISA, the Laser Interferometer. Space Antenna represents one of the most ambitious scientific instruments ever conceived. Scheduled for launch in the 2030s, LISA will consist of 3 spacecraft flying in formation millions of kilometers apart, using laser interferometry to detect gravitational waves with frequencies much lower than Earth-based detectors can observe. These low-frequency gravitational waves are produced by some of the most massive and energetic objects in the universe. Supermassive black holes, containing millions or billions of times the mass of our Sun, create powerful gravitational waves when they merge during galaxy collisions. These mergers occur over timescales of months or years, producing gravitational waves that oscillate much more slowly than the waves from stellar mass black hole collisions. LISA will be able to observe these supermassive black hole mergers from across the entire observable universe, providing a comprehensive census of how these cosmic giants form and evolve over billions of years. Each detected merger will provide another precision test of gravity's propagation speed, with some sources so distant that their gravitational waves have been traveling toward us since the universe was only a few billion years old. The space-based environment eliminates many of the noise sources that limit Earth-based detectors. There are no seismic vibrations in space, no atmospheric disturbances, no human-made interference. This pristine environment will allow LISA to achieve sensitivity levels that are impossible on Earth, potentially detecting gravitational waves from sources that are currently beyond our observational reach. But LISA will do more than just detect new types of gravitational wave sources. The mission will provide the most precise tests yet of Einstein's theory in the strong field regime, where gravitational effects are so intense that they significantly warp the fabric of space-time. These tests will search for minute deviations from general relativity that might reveal new physics beyond Einstein's framework. One of the key tests involves measuring the polarization of gravitational waves with unprecedented precision. Einstein's theory predicts that gravitational waves should have 2 specific polarization states, corresponding to the 2 ways that space-time can be stretched and squeezed as the waves pass by. Alternative theories of gravity predict additional polarization modes that would create distinctive signatures in the detected signals. The detection of unexpected polarization modes would be revolutionary, indicating that our understanding of gravity and space-time requires fundamental revision. Even if no such deviations are found, The precision of these measurements will place extraordinarily tight constraints on any modifications to Einstein's theory, ruling out vast classes of alternative theories that predict different gravitational wave properties. Pulsar timing arrays represent another frontier in gravitational wave astronomy that's already producing remarkable results. Pulsars are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. The most stable pulsars keep time more precisely than the best atomic clocks, allowing astronomers to detect tiny variations in their pulse arrival times caused by passing gravitational waves. Unlike LIGO and LISA, which detect gravitational waves directly using laser interferometry, pulsar timing arrays use the entire galaxy as a gravitational wave detector. Low-frequency gravitational waves stretching and compressing space between Earth and distant pulsars cause measurable changes in the travel time of pulsar signals, creating a galaxy-spanning detector with unprecedented sensitivity to certain types of gravitational waves. Recent results from pulsar timing arrays have detected evidence for a background of gravitational waves permeating the universe, likely produced by millions of supermassive black hole mergers occurring throughout cosmic history. This gravitational wave background represents a new form of cosmic archaeology, preserving information about the merger history of supermassive black holes across billions of years. The detection of this background provides another test of gravity's propagation speed. If gravitational waves traveled at different speeds depending on their frequency or source properties, the background would show characteristic distortions that could be detected in the pulsar timing data. The absence of such distortions confirms that gravitational waves across a wide range of frequencies all propagate at the same speed, consistent with Einstein's predictions. Future pulsar timing arrays will push these measurements to even greater precision. The planned square-kilometer array, a radio telescope network spanning multiple continents, will monitor thousands of pulsars with sensitivity levels that could detect individual supermassive black hole mergers at cosmological distances. Each detected event will provide another high-precision test of gravitational wave propagation speed. The Einstein telescope, planned as the next-generation ground-based gravitational wave detector, will represent a quantum leap in sensitivity compared to current instruments. Built underground to eliminate seismic noise and cooled to cryogenic temperatures to reduce thermal vibrations, the Einstein telescope will be able to detect gravitational waves from black hole and neutron star mergers throughout the observable universe. This unprecedented sensitivity will enable tests of gravity's speed using sources so distant that any deviations from light speed propagation would accumulate over billions of years of travel time. Even tiny differences between the speeds of gravitational waves and electromagnetic radiation would become detectable when integrated over such vast distances and timescales. The Einstein telescope will also be sensitive to new types of gravitational wave sources that current detectors cannot observe. First-generation stars, formed from primordial hydrogen and helium in the early universe, were much more massive than modern stars. When these giants collapsed into black holes, they may have produced gravitational waves with distinctive signatures that carry information about the very first generation of stars to shine in the cosmos. Cosmic strings, hypothetical, one-dimensional defects in spacetime predicted by some theories of particle physics, would produce gravitational waves with characteristic signatures unlike those from compact object mergers. If cosmic strings exist, their gravitational wave emissions could be detected by next-generation observatories, providing insights into physics at energy scales far beyond anything achievable in terrestrial laboratories. The search for primordial gravitational waves represents one of the holy grails of modern cosmology. These waves, potentially produced during cosmic inflation in the first tiny fraction of a second after the Big Bang, would carry information about the universe when it was smaller than an atomic nucleus. Detecting primordial gravitational waves would provide direct evidence for inflation and reveal details about physics at the highest energy scales imaginable. Current searches for primordial gravitational waves focus on their effect on the cosmic microwave background radiation. Gravitational waves from inflation would have left distinctive polarization patterns in this ancient light, patterns that can be searched for using sensitive microwave telescopes. Several experiments are currently operating or under development to detect these elusive signals. But future gravitational wave detectors might be able to detect primordial gravitational waves directly, without relying on their effects on electromagnetic radiation. Such a detection would represent the ultimate test of gravity's propagation speed, measuring waves that have been traveling through the universe since the very beginning of time itself. The development of quantum-enhanced gravitational wave detectors represents another exciting frontier. Current detectors are limited by quantum noise, fundamental fluctuations in the quantum vacuum that set a lower limit on the sensitivity achievable with classical measurement techniques. But quantum mechanics itself might provide ways to overcome these limitations. Squeezed light, quantum-correlated photons, and other exotic quantum states could potentially enhance the sensitivity of gravitational wave detectors beyond what's possible with classical light. These quantum technologies are already being tested in current detectors and may become standard features of future observatories. The ultimate quantum gravitational wave detector might use entangled particles or quantum field states to achieve sensitivity levels that approach fundamental limits imposed by the uncertainty principle itself. Such detectors could potentially reveal quantum properties of gravitational waves, testing whether gravity itself exhibits quantum behavior at the smallest scales. Machine learning and artificial intelligence are also transforming how we search for and analyze gravitational wave signals. Current detection algorithms rely on theoretical templates that predict the expected waveforms from various sources, but AI systems can potentially identify unexpected signals that don't match any known template. These AI-powered searches might discover new types of gravitational wave sources that produce signals too complex or exotic for traditional analysis methods. Each new type of source provides additional opportunities to test gravity's propagation speed and search for deviations from Einstein's predictions. The field of gravitational wave astronomy is advancing so rapidly that new discoveries and technological breakthroughs emerge regularly. Each advancement brings new opportunities to test the fundamental principles that govern gravity, spacetime, and causality. While every test so far has confirmed Einstein's predictions, the precision and scope of future observations will push these tests into previously unexplored regimes where new physics might finally reveal itself. The question of gravity's speed may seem settled, but science progresses by continuously challenging our assumptions and pushing the boundaries of what we can measure and understand. The next generation of gravitational wave detectors will provide the most stringent tests yet of whether gravity truly moves at the speed of light, and whether the deep connections between space, time, and causality that Einstein revealed represent the final word on these fundamental aspects of reality. At the smallest scales imaginable, where distances become comparable to the Planck length of about 10 to the negative 35 meters, and time intervals approach the Planck time of about 10 to the negative 44 seconds, our familiar notions of space, time, and speed may break down completely. In this quantum realm of gravity, the very concepts we use to understand gravitational wave propagation might require fundamental revision. Einstein's general relativity describes gravity as the curvature of smooth, continuous space-time. But quantum mechanics suggests that at the smallest scales, this smooth geometry might give way to a seething foam of quantum fluctuations, where space and time themselves become uncertain and probabilistic. In this quantum space-time, the meaning of gravitational wave propagation, and even the concept of a definite propagation speed, becomes profoundly ambiguous. The search for a quantum theory of gravity represents one of the greatest challenges in modern physics. Unlike the other fundamental forces, which have been successfully unified with quantum mechanics, gravity has resisted all attempts at quantization. The mathematical frameworks that work so well for describing electromagnetic, weak and strong nuclear forces encounter fundamental difficulties when applied to the geometric nature of gravitational interactions. One of the leading approaches to quantum gravity involves the hypothetical graviton, a quantum particle that would carry gravitational interactions just as photons carry electromagnetic interactions. If gravitons exist, they would be massless particles that travel at exactly the speed of light, providing a quantum mechanical explanation for why gravitational effects propagate at light speed in Einstein's classical theory. But gravitons, if they exist, would be extraordinarily difficult to detect directly. The weakness of gravitational interactions means that individual gravitons would have incredibly tiny effects on matter, far below the detection threshold of any conceivable experiment. We experience gravity as a classical phenomenon because it involves the collective behavior of countless gravitons, just as we experience electromagnetic fields as classical phenomena, even though they're ultimately composed of photons. The quantum properties of gravitons could potentially lead to subtle deviations from classical predictions about gravitational wave propagation. Quantum effects might introduce tiny variations in propagation speed that depend on the energy or frequency of gravitational waves, creating a form of quantum dispersion that could be detectable with sufficiently sensitive instruments. Loop quantum gravity offers a radically different approach to quantizing spacetime. Instead of treating gravity as a force carried by particles, loop quantum gravity attempts to quantize the geometry of spacetime itself. In this framework, space is not continuous, but is instead composed of discrete, atom-like units connected in a complex network structure. If loop quantum gravity is correct, then gravitational waves would not propagate through smooth spacetime, but would instead represent excitations traveling through this discrete quantum geometry. The propagation speed might depend on the wavelength of the gravitational waves relative to the fundamental scale of the quantum spacetime network, potentially leading to measurable deviations from the classical speed of light. The discrete nature of quantum spacetime could also introduce fundamental limits on how precisely we can measure or even define the speed of gravitational wave propagation. If space and time themselves become uncertain at the smallest scales, then the concept of a precise propagation speed might lose its meaning, replaced by probability distributions that describe the likelihood of detecting gravitational effects at different times and locations. String theory, perhaps the most ambitious attempt to unify gravity with quantum mechanics, suggests that all fundamental particles, including gravitons, are tiny vibrating strings existing in a higher dimensional spacetime. Different vibrational modes of these strings correspond to different particles, with gravitons representing one particular type of string vibration. In string theory, the propagation of gravitational effects would depend on the dynamics of strings moving through the higher dimensional bulk spacetime. If our familiar three-dimensional space is embedded in a higher dimensional reality, gravitational waves might propagate through dimensions that are inaccessible to other particles, potentially allowing for propagation speeds that differ from the speed of light in our three-dimensional world. However, most versions of string theory preserve the light speed limit for gravitational propagation, at least in the low energy limit that corresponds to our everyday experience. The theory's consistency requirements, including the need to preserve unitarity and avoid mathematical anomalies, typically force gravitational effects to propagate at the fundamental speed limit of the theory's spacetime geometry. Causal set theory proposes that spacetime is fundamentally discrete, composed of elementary units of space and time arranged in a network structure that preserves causal relationships. In this framework, the propagation of gravitational effects would involve information hopping from one spacetime element to its causally connected neighbors, with the speed of propagation determined by the density and connectivity of the causal network. If spacetime is indeed a causal set, then the apparent continuity of classical spacetime would emerge only at scales much larger than the fundamental discreteness scale. Gravitational waves would represent collective excitations propagating through the causal network, with their macroscopic speed determined by the microscopic structure of space-time itself. The holographic principle, inspired by the physics of black holes, suggests that all information in a volume of space can be encoded on its boundary. This principle has profound implications for understanding gravitational wave propagation, as it implies that three-dimensional gravitational dynamics might be equivalent to two-dimensional physics occurring on distant boundaries. In holographic theories, the propagation of gravitational waves through three-dimensional space might be mathematically equivalent to the evolution of quantum fields on a two-dimensional surface. The speed of gravitational wave propagation would then be related to the speed of information processing on this holographic boundary, connecting gravity's speed to fundamental limits on quantum information transmission. Emergent gravity theories propose that gravitational interactions might not be fundamental, but could instead emerge from more basic quantum mechanical processes, similar to how thermodynamic properties like temperature and pressure emerge from the statistical behavior of many particles. If gravity is emergent, then its propagation speed might not be a fundamental constant, but could instead depend on the underlying quantum processes that give rise to gravitational phenomena. In some emergent gravity models, the speed of gravitational effects could vary with energy scale or environmental conditions, potentially leading to observable deviations from Einstein's predictions. These theories often predict that gravity's apparent universality and constant propagation speed are approximations that hold only in certain limits or under specific conditions. The black hole information paradox illustrates some of the deepest puzzles in quantum gravity that relate to information propagation. When matter falls into a black hole, quantum mechanics suggests that information about that matter cannot be destroyed, but general relativity indicates that the information disappears beyond the event horizon and is eventually destroyed when the black hole evaporates. Various proposed solutions to this paradox involve radical revisions to our understanding of how information propagates in space-time. Some theories suggest that information can escape from black holes through quantum tunneling effects that occur faster than light, while others propose that the information is encoded in correlations between particles that are separated at light speed, but remain quantum mechanically entangled. The resolution of the black hole information paradox may require a complete rethinking of how information and causality work in quantum gravity, potentially changing our understanding of what it means for gravitational effects to propagate at a definite speed through space-time. Quantum field theory in curved space-time, the framework used to study quantum effects in strong gravitational fields, reveals additional subtleties in how we understand gravitational wave propagation. In this framework, the vacuum state of quantum fields can become excited by changing gravitational fields, creating particles and antiparticles from empty space. This process, known as particle creation by gravitational fields, means that gravitational waves carry energy not just through their classical stretching and squeezing of spacetime, but also through their ability to excite quantum vacuum fluctuations. The speed at which this quantum energy propagates might differ subtly from the speed of the classical gravitational wave itself. The study of Hawking radiation from black holes reveals another connection between quantum mechanics and gravitational information propagation. Black holes emit thermal radiation due to quantum effects near their event horizons, and this radiation carries away information about the black hole's properties at a rate that depends on the black hole's surface area and temperature. The speed at which Hawking radiation carries information away from black holes is limited by the speed of light, but the quantum mechanical process that creates this radiation involves virtual particles and quantum fluctuations that operate according to different rules than classical gravitational wave propagation. Understanding these quantum effects is crucial for developing a complete theory of how information propagates in quantum gravity. ADS-CFT correspondence one of the most important developments in theoretical physics over the past few decades, establishes a precise mathematical relationship between quantum gravity in higher dimensional curved spacetime and quantum field theories on lower dimensional flat boundaries. This correspondence provides a powerful tool for studying quantum gravitational phenomena that would otherwise be intractable. In the ADS-CFT framework, gravitational wave propagation in the higher dimensional bulk spacetime corresponds to specific types of excitations in the lower dimensional boundary theory. The speed of gravitational wave propagation in the bulk is related to the speed of information transmission in the boundary theory, providing new insights into the fundamental limits on how fast gravitational information can travel. The correspondence also reveals that quantum entanglement between different regions of the boundary theory is geometrically represented by connections through the higher dimensional bulk spacetime. This suggests deep relationships between quantum information, spacetime geometry, and the propagation of gravitational effects that are still being explored by theoretical physicists. Quantum error correction, a field originally developed for protecting quantum information in quantum computers, has found surprising applications in quantum gravity. Some researchers propose that spacetime itself might function as a quantum error, correcting code, with gravitational dynamics serving to protect quantum information from corruption by environmental interference. If spacetime is indeed a quantum error correcting system, then the propagation of gravitational waves might be understood as the transmission of quantum information through this protective encoding. The speed of gravitational wave propagation would then be related to fundamental limits on quantum error correction and information processing in quantum gravitational systems. These quantum perspectives on gravity raise profound questions about whether the concept of propagation speed has the same meaning in quantum gravity as it does in classical physics. At the quantum level, particles don't follow definite trajectories, but instead exist in superposition states that encompass multiple possible paths simultaneously. Gravitational waves, if they are quantum mechanical phenomena, might not have well-defined propagation speeds, but could instead be characterized by probability distributions over different possible speeds and arrival times. The measurement process in quantum mechanics could play a crucial role in determining the observed speed of gravitational wave propagation. Before detection, gravitational waves might exist in quantum superposition states that include components propagating at different speeds. The act of detection could collapse this superposition, forcing the gravitational wave to manifest with a specific speed that depends on the details of the measurement process itself. When we say that gravity moves at the speed of light, we're making an assumption that might seem obvious, but is actually deeply philosophical. We're assuming that concepts like speed, movement, and propagation have clear, unambiguous meanings when applied to the fabric of spacetime itself. But Einstein's revolution in our understanding of gravity forces us to question these basic intuitions and confront some of the most profound puzzles about the nature of reality. In our everyday experience, speed refers to how fast an object moves through space over time. A car travels down a highway, covering distance at a measurable rate. Light races through empty space from distant stars to our eyes. These familiar examples involve objects or disturbances moving through a pre-existing spatial framework, with time providing the backdrop against which we measure their motion. But gravitational waves represent something fundamentally different. They are not objects moving through spacetime. They are disturbances in spacetime itself. When we detect a gravitational wave, we're observing space and time stretching and compressing as the wave passes by. The speed of gravity is really the speed at which changes in spacetime geometry propagate from one location to another. This creates a conceptual puzzle that has fascinated philosophers and physicists since Einstein first proposed his geometric theory of gravity. If spacetime is the arena in which all motion occurs, what does it mean for spacetime itself to move or change? How can we define the speed of something when that something is the very framework we use to define speed. Consider the analogy of ripples spreading across the surface of a pond. We can easily understand the speed of these ripples because we observe them from outside the pond, measuring their motion against a fixed reference frame provided by the pond's edges and our external vantage point. But with space-time, there is no external vantage point. We are embedded within the very medium whose motion we're trying to understand. This embedded perspective creates deep philosophical questions about the nature of measurement and observation in Einstein's universe. When LIGO detects a gravitational wave, the stretching of space-time affects both the laser light used for detection and the rulers we might use to measure that stretching. The gravitational wave changes the geometry of space in which the measurement is taking place, creating a subtle but profound observer effect that challenges our intuitive understanding of objective measurement. From the perspective of someone riding along with a gravitational wave, space-time appears perfectly normal and unchanging. It's only when we compare measurements taken at different locations that we can detect the wave's passage. This relativity of gravitational effects mirrors the relativity of motion that Einstein discovered in his special theory of relativity, where motion has meaning only in relation to chosen reference frames. The philosophical implications extend beyond technical questions about measurement to touch on fundamental issues about the nature of causation itself. In Newton's universe, gravitational force acted instantly across space, creating a clear causal relationship between distant objects. The Sun's gravitational field reached out across 93 million miles to hold Earth in its orbit, establishing an unambiguous causal connection between solar mass and planetary motion. Einstein's geometric gravity complicates this picture. Earth doesn't orbit the Sun because of a force reaching across space. It follows the straightest possible path through the curved space-time created by the Sun's presence. The curvature that guides Earth's motion was established by the Sun's mass in the past, not by any instantaneous action in the present. This temporal separation between cause and effect introduces new subtleties into how we understand gravitational causation. When massive objects accelerate somewhere in the universe, they create gravitational waves that carry information about their motion outward at light speed. But this information represents the past state of those objects, not their current condition. By the time gravitational waves from a distant black hole collision reach Earth, billions of years might have passed since the original event. The gravitational wave carries with it a kind of fossil record of ancient cosmic violence, preserved in the stretching and squeezing of space-time itself. This raises profound questions about the relationship between past and present in gravitational interactions. Are the gravitational effects we experience today caused by the current state of distant massive objects, or by their past states as recorded in the gravitational waves and space-time curvature reaching us now? The answer depends on subtle philosophical distinctions about what we mean by causation in a universe where information propagates at finite speed. The finite speed of gravitational propagation also affects how we understand the unity and coherence of physical systems. In Newton's universe, gravitational forces could coordinate the behavior of widely separated objects instantaneously, maintaining precise relationships between planetary motions across vast distances. The solar system functioned as a unified, coherent mechanism despite the enormous spaces between its component parts. Einstein's light speed limit for gravity introduces delays and coordination problems that challenge this mechanistic view. Different parts of a gravitational system receive information about changes in other parts only after delays determined by the finite speed of gravitational wave propagation. This creates a more complex, distributed form of gravitational coherence where perfect synchronization is impossible across large distances. Consider the dance of binary stars spiraling inward toward collision. Each star responds to gravitational information about its companion's position and motion, But this information reflects where the companion was in the past, not where it is now. The resulting orbital dynamics involve a complex interplay between current conditions and historical information, creating a form of gravitational memory that influences present behavior. This temporal complexity in gravitational interactions has implications for how we understand personal identity and continuity across time. If gravitational effects carry information about past states of massive objects, then the gravitational field surrounding us contains traces of the entire history of matter and energy in our cosmic neighborhood. In a sense, we are constantly immersed in gravitational memories of the past, experiencing the accumulated influence of countless ancient events. The observer dependence of gravitational effects raises questions about the objective reality of space-time curvature. Different observers, moving at different velocities or located in different gravitational fields, will measure different values for the curvature of space-time at the same event. These measurements are related by precise mathematical transformations, but they are nonetheless different, raising questions about which measurement, if any, represents the true curvature. This relativity of space-time geometry mirrors broader philosophical questions about the nature of physical properties in a relativistic universe. If different observers disagree about basic features of space-time, such as the simultaneity of distant events or the geometry of spatial regions, what does this tell us about the objective reality of these features? Are they merely artifacts of observation and measurement? Or do they reflect deeper truths about the nature of reality itself? The holographic principle, emerging from studies of black hole physics and quantum gravity, suggests even more radical revisions to our understanding of spatial and temporal relationships. If all information in a three-dimensional volume can be encoded on its two-dimensional boundary, then the apparent three-dimensionality of space might be a kind of illusion, with the fundamental physics occurring on lower dimensional surfaces. In holographic theories, the propagation of gravitational waves through three-dimensional space might be equivalent to information processing on distant two-dimensional boundaries. The speed of gravity would then refer not to motion through space, but to the rate of information transmission across these holographic surfaces. This perspective challenges our basic intuitions about space, dimension, and the meaning of motion itself. Quantum mechanics introduces additional philosophical complexities through the fundamental role of measurement and observation in determining physical properties. In quantum gravitational theories, space-time geometry itself might exist in superposition states before measurement, encompassing multiple possible configurations simultaneously. The act of detecting a gravitational wave could collapse this superposition, forcing space-time to manifest with specific geometric properties. If quantum mechanics applies to gravity and space-time, then the speed of gravitational wave propagation might not be a definite, objective property, but rather something that depends on how and when we choose to measure it. Different measurement strategies could reveal different aspects of gravitational wave propagation, challenging the classical notion of speed as an intrinsic property independent of observation. The relationship between mathematics and physical reality becomes particularly subtle when discussing the speed of gravity. Einstein's field equations make precise predictions about gravitational wave propagation speeds, but these equations describe mathematical relationships between abstract geometrical objects rather than direct physical mechanisms. The question of whether gravitational waves really propagate at light speed, or whether this speed is merely a feature of our mathematical description, touches on deep philosophical issues about the nature of mathematical truth in physics. Some philosophers argue that physical theories like general relativity should be understood instrumentally, as useful tools for predicting observations rather than literal descriptions of reality. From this perspective, the statement that gravity moves at light speed is meaningful only insofar as it helps us predict the results of gravitational wave detections and other experiments. Others contend that successful physical theories reveal genuine truths about the structure of reality, making the speed of gravitational wave propagation a real, objective feature of the universe. The philosophical debate between these instrumentalist and realist interpretations affects how we understand the significance of measuring gravity's speed and the implications of potential deviations from Einstein's predictions. The emergence of space-time from more fundamental quantum processes, suggested by various approaches to quantum gravity, raises questions about whether concepts like speed and propagation have meaning at the most fundamental level of reality. If space and time themselves emerge from quantum information processing or other non-spatiotemporal phenomena, then the speed of gravity might be a derived property rather than a fundamental feature of nature. These emergent theories suggest that our familiar concepts of space, time, and motion might be approximate descriptions that apply only at scales much larger than the fundamental quantum gravitational scale. At the deepest level, reality might be organized according to principles that have nothing to do with spatial motion or temporal progression, making questions about gravitational propagation speed ultimately meaningless or obsolete. The philosophical implications of gravity's speed thus extend far beyond technical questions in physics to encompass fundamental issues about the nature of reality, causation, observation, and mathematical truth. As we continue to refine our measurements of gravitational wave propagation and develop new theories of quantum gravity, we are simultaneously exploring some of the deepest questions that human beings can ask about the nature of existence itself. After journeying through the depths of Einstein's theory, quantum mechanics, and philosophical speculation, we return to a fundamental truth that shapes every moment of cosmic evolution. Gravity moves at the speed of light, and this simple fact continues to orchestrate the grandest symphony of matter, energy, space, and time across the entire observable universe. Every piece of evidence we have gathered, from the collision of black holes billions of light years away to the precise orbital decay of binary pulsars in our own galaxy, confirms that gravitational effects propagate at exactly the cosmic speed limit. This is not merely an abstract theoretical prediction, but a concrete physical reality that determines how galaxies form, how stars live and die, and how the universe itself evolves across billions of years. The detection of gravitational waves has transformed this theoretical insight into direct observational fact. When LIGO and Virgo detect the merger of two black holes, they are not just confirming Einstein's century-old predictions about space-time geometry. They are witnessing the universe's fundamental communication system in action, observing how cosmic events send information rippling through the fabric of reality at precisely the speed that maintains causality and preserves the logical structure of physical law. The precision of these measurements is staggering. The gravitational waves and light from the neutron star, merger GW 170817, arrived within less than 2 seconds of each other after traveling for 130 million years. This synchronization, precise to a few parts in a quintillion, represents one of the most stringent tests of fundamental physics ever achieved. It demonstrates that gravity's speed limit is not approximate but exact, woven into the very foundations of how reality operates. This precision has profound implications for our understanding of the universe's architecture. If gravitational effects could propagate even slightly faster than light, the delicate balance of cosmic evolution would be fundamentally altered. Galaxy formation, stellar nucleosynthesis, planetary system stability, and the emergence of complex structures capable of supporting life all depend on the precise timing relationships established by gravity's light-speed propagation. The cosmic web of dark matter that provides the scaffolding for all visible structures formed according to patterns established by gravitational wave propagation across billions of years. The filaments of matter stretching between galaxy clusters, the voids that separate these cosmic highways, and the hierarchical clustering that produces everything from globular clusters to superclusters, all reflect the finite speed at which gravitational information travels through expanding space-time. Without this speed limit, the universe would look fundamentally different. Instantaneous gravitational action would have allowed structures to form too quickly in the early universe, potentially preventing the gradual hierarchical assembly that produced the rich variety of cosmic architectures we observe today. Faster than light gravity might have created runaway collapse scenarios where matter clumped together too efficiently, leaving behind a universe of black holes rather than the diverse ecosystem of stars, planets, and galaxies that actually exists. The speed of gravity also ensures that the universe maintains its democratic character, where no reference frame is privileged over any other. This relativity principle, built into the very propagation of gravitational effects, guarantees that the laws of physics look the same to all observers, regardless of their motion through space. This symmetry is not just an abstract mathematical property, but a practical reality that affects everything from GPS satellite navigation to particle accelerator experiments. Every time we use technology that depends on precise timing or navigation, we rely implicitly on the fact that gravitational effects propagate at light speed. The GPS satellites orbiting Earth must account for both special and general relativistic effects, including the finite speed of gravitational wave propagation, to maintain the precision needed for accurate positioning. The speed of gravity is literally built into the infrastructure of modern technological civilization. The continuing search for deviations from Einstein's predictions serves an important function, even as each new observation confirms the light speed propagation of gravitational effects. Science advances not just by confirming existing theories, but by pushing the boundaries of measurement precision to explore regimes where new physics might reveal itself. The absence of any detected deviations, measured to ever greater precision, places increasingly stringent constraints on alternative theories and speculative modifications to general relativity. Future gravitational wave observations will extend these tests to even more extreme regimes. The planned LISA Space Observatory will detect gravitational waves from supermassive black hole mergers occurring when the universe was only a few billion years old, testing gravity's propagation speed over cosmological distances and timescales. The Einstein telescope will achieve sensitivity levels that could detect primordial gravitational waves from cosmic inflation, potentially revealing information about gravity's behavior in the first moments after the Big Bang. Each new detection adds another data point to the overwhelming case that gravity moves at light speed, but it also opens new windows into cosmic phenomena that we have never observed before. Gravitational wave astronomy is still in its infancy, comparable to where electromagnetic astronomy was when Galileo first turned a telescope toward the heavens. The discoveries yet to come will undoubtedly surprise us, but they will also continue to test the fundamental principles that govern space-time, causality, and information propagation throughout the cosmos. The robustness of Einstein's predictions about gravity's speed reflects the deep interconnectedness of physical law. The speed of gravitational wave propagation is not an isolated fact, but emerges from the same principles that govern electromagnetic radiation, the structure of space-time, and the relationship between matter and geometry. This unity suggests that we have uncovered something profound about the underlying architecture of reality, a set of principles so fundamental that they constrain all physical phenomena. The philosophical implications of this unity extend beyond physics into questions about the nature of scientific knowledge itself. The fact that diverse phenomena, from the behavior of atomic clocks to the collision of black holes, all conform to the same underlying principles suggests that the universe operates according to comprehensible mathematical laws. This comprehensibility is not guaranteed. It represents a remarkable and perhaps mysterious feature of reality that makes scientific understanding possible. The speed of gravity also plays a crucial role in connecting different scales of physical reality. The same light speed limit that governs gravitational wave propagation from cosmic collisions also determines the maximum rate at which information can flow in quantum systems. The speed of electromagnetic radiation from atomic transitions, and the causal structure of space-time at all scales. This universal speed limit creates a kind of cosmic democracy where all physical processes, regardless of their scale or nature, must respect the same fundamental constraint. Looking toward the future, gravitational wave astronomy promises to reveal aspects of the universe that have remained hidden since the beginning of time. The gravitational wave background from cosmic inflation could carry information about the universe when it was smaller than an atomic nucleus, potentially revealing details about the quantum origin of space and time themselves. Observations of this primordial background would provide the ultimate test of gravity's propagation speed, measuring waves that have been traveling since the very first moments of cosmic history. The development of quantum gravitational wave detectors might eventually allow us to observe individual gravitons, the quantum particles that carry gravitational interactions. Such observations would bridge the gap between Einstein's classical theory and quantum mechanics, potentially revealing whether the concept of gravitational wave speed retains its meaning at the quantum level or requires fundamental revision. But even as we push toward these exotic frontiers, the basic fact remains unchanged. Every observation, every experiment, every theoretical analysis continues to confirm that gravitational effects propagate at the speed of light. This consistency across vastly different physical regimes suggests that we have uncovered a truly fundamental aspect of how the universe works, one that will likely survive whatever theoretical revolutions the future might bring. The story of gravity's speed is ultimately a story about the limits and possibilities of physical reality. The cosmic speed limit does not represent a constraint or limitation on what the universe can accomplish, but rather the organizing principle that makes complex, coherent, causally connected structures possible in the first place. Without this speed limit, the universe might be a chaos of instantaneous interactions, where cause and effect lose their meaning and organized complexity cannot emerge. Instead, we live in a universe where information travels at finite speed, where the past influences the present in orderly ways, where distant events require time to make their effects felt, and where the arrow of time has clear meaning. These features, all consequences of gravity's light speed propagation, create the conditions necessary for stars to shine steadily, planets to maintain stable orbits, and complex chemical and biological processes to evolve over cosmic time. The speed of gravity thus represents more than a technical detail in Einstein's theory. It embodies the fundamental principle that makes our universe a place where structure, complexity, and ultimately life itself can exist and flourish. Every gravitational wave detection, every precision test of general relativity, and every theoretical exploration of quantum gravity adds new chapters to our understanding of this principle. But the central truth remains constant. Gravity moves at the speed of light, and this fact continues to shape every aspect of cosmic evolution, from the smallest quantum scales to the largest structures in the observable universe. The answer, confirmed by decades of increasingly precise observations, is clear and definitive. Gravity moves at the speed of light, not faster, not slower, but at exactly the same cosmic speed limit that governs all information propagation throughout the universe. This is not merely a theoretical prediction, but an experimentally verified fact, tested to precision levels that would have been unimaginable when Einstein first proposed his revolutionary theory of curved spacetime. Yet this simple answer carries profound implications that extend far beyond the technical details of general relativity. The speed of gravity shapes the causal structure of reality itself, determining which events can influence others and establishing the boundaries between past, present, and future across the cosmos. It ensures that cause precedes effect, that information cannot travel backward in time, and that the universe maintains a coherent logical structure despite its vast scale and complexity. Every gravitational wave detection adds new confirmation to this fundamental truth, while simultaneously opening new windows into cosmic phenomena we have never observed before. The collision of black holes billions of light years away, the merger of neutron stars that forge heavy elements in unimaginable violence, the potential whispers of gravitational waves from the first moments after the Big Bang itself, all carry their information to us at precisely the speed that maintains the universe's causal coherence. The precision of these measurements represents one of humanity's greatest intellectual achievements. When we detect gravitational waves and electromagnetic radiation from the same cosmic event arriving within seconds of each other after traveling for millions of years, we are witnessing the universe's fundamental communication system operating with clockwork precision across scales that dwarf human comprehension. This synchronization, accurate to parts per quintillion, demonstrates that we have uncovered something truly fundamental about the architecture of reality. But our exploration has also revealed the boundaries of current knowledge and the mysteries that continue to challenge our understanding. Quantum gravity remains an unsolved puzzle, and we do not yet know how the concepts of space, time, and propagation speed might require revision in a complete quantum theory of gravitational phenomena. The discrete structure of space-time at the Planck scale, the holographic encoding of information on cosmic boundaries, and the emergence of classical physics from quantum foundations all suggest that even deeper revolutions in our understanding may lie ahead. The philosophical implications of gravity's speed touch some of the most fundamental questions about the nature of reality, causation, and knowledge itself. If space-time is not a fixed stage, but a dynamic participant in cosmic drama, what does it mean for changes in space-time geometry to propagate at a definite speed? How do we measure the motion of the very framework we use to define motion? These questions probe the foundations of scientific measurement and challenge our intuitive understanding of space, time, and physical causation. The search for faster-than-light gravitational effects, while unsuccessful so far, serves an important function in science by pushing theoretical possibilities to their limits and testing the boundaries of established knowledge. Each negative result, each confirmation of light speed propagation, narrows the range of viable alternatives and strengthens our confidence in the fundamental principles that govern space-time dynamics. The absence of any detected deviations from Einstein's predictions, despite increasingly sensitive searches, suggests that we have indeed discovered something profound about the universe's basic operating principles. Future observations promise to extend these tests into previously unexplored regimes. Space-based gravitational wave detectors will observe supermassive black hole mergers from across cosmic history. Pulsar timing arrays will map the gravitational wave background created by millions of cosmic collisions. And next-generation instruments may detect primordial gravitational waves, carrying information about the universe's quantum origin. Each new detection will provide another precision test of gravity's speed, while simultaneously revealing new aspects of cosmic evolution. The technological applications of gravitational wave astronomy are only beginning to be explored. Just as electromagnetic astronomy led to revolutionary technologies from radio communication to medical imaging, gravitational wave detection may spawn innovations we cannot yet imagine. The quantum sensors and precision measurement techniques developed for gravitational wave detection are already finding applications in other fields, demonstrating how fundamental research continues to drive technological progress. The speed of gravity also connects to broader questions about the unity and comprehensibility of physical law. The fact that gravitational waves, Electromagnetic radiation and other fundamental phenomena all respect the same cosmic speed limit, suggests a deep underlying unity in nature's laws. This unity is not guaranteed or obvious. It represents a remarkable feature of reality that makes scientific understanding possible and meaningful. The cosmic speed limit creates a kind of democracy in the universe where no reference frame is privileged, and all observers, regardless of their motion, discover the same fundamental laws of physics. This principle of relativity, embodied in the propagation speed of gravitational effects, ensures that the universe operates according to consistent rules that can be discovered and understood through careful observation and theoretical analysis. The story of measuring gravity's speed also illustrates the power and beauty of the scientific method itself. A theoretical prediction made over a century ago has been confirmed through some of the most sophisticated technological achievements in human history. The laser interferometers that detect gravitational waves represent the culmination of decades of engineering innovation, theoretical development, and international collaboration, demonstrating humanity's capacity to probe nature's deepest secrets through ingenuity and persistence. Yet science is never complete or final. Each answer opens new questions, each discovery reveals new mysteries, and each precision measurement pushes us toward the boundaries of current knowledge where new physics may await discovery. The confirmation that gravity moves at light speed is simultaneously a triumph of current understanding and a foundation for future explorations that may revolutionize our view of reality once again. The invisibility of gravitational waves in our everyday experience reminds us how much of reality remains hidden from direct perception. The universe is filled with information flowing at light speed through dimensions of space-time that our senses cannot detect, carrying news of cosmic violence and creation across billions of years and billions of light years. We live immersed in this sea of gravitational information, most of which passes by us unnoticed, a reminder of how much mystery remains in even the most familiar aspects of our cosmic environment. As we look toward the future, gravitational wave astronomy promises to become as fundamental to our understanding of the cosmos as traditional electromagnetic astronomy has been for centuries. We are witnessing the birth of a new field that may ultimately reveal aspects of the universe that have remained hidden since the beginning of time itself. The gravitational waves rippling through space around us carry stories of cosmic evolution that we are only beginning to learn how to read. The speed of gravity represents more than a technical parameter in Einstein's equations. It embodies the fundamental principle that information, causality, and physical law operate according to comprehensible rules throughout the observable universe. This comprehensibility is itself mysterious and wonderful, suggesting that reality is organized according to mathematical principles that human minds can discover, understand, and appreciate. In the end, our exploration of gravity's speed has taken us on a journey through some of the most profound territories of human knowledge, from the practical challenges of building gravitational wave detectors to the deepest philosophical questions about the nature of space, time, and causation. The answer to our original question turns out to be both simple and profound. Gravity moves at the speed of light, preserving causality and connecting every part of the universe to every other part through the invisible threads of space-time geometry. The speed of gravity shapes not just how things move, but how reality connects across space and time, creating the cosmic web of cause and effect that makes our existence possible. In understanding this speed, we glimpse something fundamental about the universe's deepest architecture, a glimpse that fills us with wonder at the elegant mathematical harmony that governs the cosmos and our place within it.